Hello, wonderful souls. Welcome back to another journey through the cosmos, where science becomes a lullaby and the universe whispers its secrets just for you. Tonight, we're embarking on something extraordinary, a voyage to the coldest corners of existence itself. Imagine a place so cold that atoms nearly stop moving, a realm where the frantic dance of molecules that gives us warmth, sound, and life itself slows to an almost perfect stillness. Picture the universe holding its breath frozen in a moment that stretches toward eternity. These places exist. They're real. And tonight, we're going to find them together. If you're ready to drift through the frozen beauty of the cosmos with us, go ahead and hit that like button. And if you haven't subscribed yet, join our community of curious dreamers who find peace in understanding the magnificent universe we call home. Your presence here means everything. Now, let me ask you something. What is cold really? We bundle up in winter, we shiver when the temperature drops. We think we understand what it means to be cold. But here's the beautiful truth that most people never consider. Cold isn't actually a thing at all. There's no such thing as cold energy or cold particles flowing into your body on a winter day. Cold is simply the absence of something else. It's the absence of heat, the absence of movement, the absence of that invisible dance happening in every atom around us right now. Think about it this way. Right now, as you're listening to these words, the air molecules around you are moving at about 500 meters per second. That's faster than the speed of sound. They're colliding with each other millions of times every second, bouncing off your skin, creating what we call temperature. Heat isn't a substance, it's motion. It's kinetic energy. It's the universe in perpetual movement. And when we talk about something being cold, we're really talking about that movement slowing down. Temperature is simply a measurement of how fast particles are moving. When something is hot, its molecules are vibrating, rotating, and bouncing around with tremendous energy. A boiling pot of water contains molecules moving so frantically that they're escaping into the air as steam. A piece of ice has molecules still moving, but much more slowly locked into crystalline patterns that we can actually see. And when we create something incredibly colder than anything in nature, we're essentially trying to slow that movement down further and further approaching, but never quite reaching a perfect stillness. This brings us to one of the most profound concepts in all of physics: absolute zero. On the Celsius scale, we call it minus 273.15 degrees. On the Fahrenheit scale, it's minus 459.67 degrees. But scientists prefer the Kelvin scale, where absolute zero is simply zero, because it represents a genuine zero, a fundamental limit of nature itself. At absolute zero, all thermal motion stops completely. It's the coldest possible temperature. Not the coldest we've achieved, but the coldest that can theoretically exist. And here's what makes this so hauntingly beautiful: we can never actually reach it. Not completely. It's written into the laws of physics themselves. The third law of thermodynamics tells us that as a system approaches absolute zero, it becomes increasingly difficult to remove more energy. It's like trying to empty a bucket that somehow generates more water the emptier it gets. We can get incredibly close. Scientists have cooled atoms to billionths of a degree above absolute zero. But that final distance is an infinity we can never cross. Why? Because of something extraordinary called the Heisenberg uncertainty principle. This quantum rule tells us that we can never know both the exact position and exact momentum of a particle simultaneously. If we somehow manage to cool atoms to true absolute zero, they would have zero kinetic energy, which means we'd know their momentum precisely. And if we know their momentum precisely, their position becomes completely uncertain. They could be anywhere in the universe. The atom would stop being a localized thing at all. Reality itself prevents absolute stillness from existing. But let's talk about what happens when we get close, because the behavior of matter near absolute zero is nothing short of magical. Take superconductivity, for instance. When certain materials are cooled to extremely low temperatures, something remarkable happens. They lose all electrical resistance. Completely. You could start an electrical current flowing through a superconducting ring, remove the power source, and that current would continue flowing forever, literally forever. Scientists have created superconducting currents that have flowed undiminished for years, with no signs of stopping. In these materials, electrons pair up in a quantum dance and glide through the atomic lattice without any friction whatsoever. Then, there's superfluidity, perhaps one of the strangest phenomena in all of nature. Cool liquid helium to about 2 Kelvin, and it transforms into something that seems to defy the laws of physics. A superfluid has zero viscosity, no internal friction at all. If you put a superfluid in a container, it will creep up the walls, flow over the edge, and drip down the outside all on its own, driven by quantum effects. It can flow through holes so tiny that ordinary liquids couldn't possibly pass through. It doesn't obey the normal rules. A superfluid in a very real sense is a macroscopic quantum object. A substance where quantum mechanics usually confined to the atomic scale becomes visible to the naked eye. And if we go even colder, we encounter Bose-Einstein condensates. At temperatures within a few billionths of a degree above absolute zero, certain groups of atoms lose their individual identities. They stop being thousands of separate particles and become a single quantum entity. Imagine a stadium full of people suddenly moving, thinking and acting as one perfect organism. That's what happens to atoms in a Bose-Einstein condensate. They occupy the same quantum state, the same space, the same existence. Einstein predicted this phenomenon in 1924, but it took scientists until 1995 to actually create one. And when they did, they opened a window into a realm of physics we're still trying to understand. Now, here's something most people get wrong about space, about the cosmic void between planets and stars. We often hear that space is cold, and in a sense that's true, but space isn't cold the way a winter night is cold. In fact, if you were floating in space unprotected, you wouldn't freeze immediately. You'd actually have a harder time getting rid of heat than staying warm. Why? Because cold requires something that can absorb your heat. When you're cold on Earth, it's because air molecules are bouncing off your skin, carrying away your body heat. But in the vacuum of space, there are almost no molecules. There's nothing to conduct your heat away. The only way you'd lose heat is through radiation, slowly emitting infrared light into the void. You'd freeze eventually, but it would take time. The temperature of empty space itself is about 2.7 Kelvin or minus 270 degrees Celsius. That's the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. It's the leftover heat from the moment the universe was born, now cooled by 13.8 billion years of expansion. Every cubic centimeter of space is bathed in this ancient light, stretched by the expansion of the universe from blazing gamma rays into faint microwaves. We can't see it with our eyes, but it's there, a whisper from the beginning of everything, telling us that even the darkest, emptiest reaches of space aren't quite at absolute zero. But within this vast cosmic coldness, there are pockets that are colder still. Places where nature has created conditions even more extreme than the average temperature of space. There are objects so far from any star, so isolated in the cosmic dark, that they've cooled to temperatures barely above absolute zero. There are nebulae where the gas is expanding so rapidly that it cools itself to temperatures lower than the background radiation of space itself. And then there are the experiments we've created here on Earth, in laboratories where scientists battle against every law of thermodynamics to create the coldest temperatures in the known universe. In these labs, matter behaves in ways that seem impossible, revealing the quantum foundations of reality itself. We've created temperatures colder than the darkest reaches of intergalactic space, colder than anything nature has produced, purely to glimpse the strange and beautiful physics that emerges when motion nearly stops. So, tonight we're going to explore this landscape of cold. We'll travel from the frozen extremes of our own planet to the ice worlds of the outer solar system. We'll drift through the space between stars, where ancient light barely warms the darkness. We'll discover objects floating alone in the cosmic void, so cold they challenge our understanding of what's possible. And we'll contemplate the far future, when the universe itself may cool to near absolute zero, and the last stars flicker out in an eternal night. But we'll also discover something unexpected along the way. In the coldest places, we sometimes find the most interesting things: moons with hidden oceans, clouds where new stars are being born, quantum states that exist nowhere else. And perhaps most importantly, we'll gain a deeper appreciation for warmth, for the movement and energy and life that makes our small corner of the universe so impossibly special. Take a deep breath. Settle in. Let the ordinary concerns of the day drift away, because we're about to discover that cold isn't emptiness or death or absence. It's a doorway, a threshold, a place where the universe reveals secrets it keeps hidden everywhere else. And our first step on this journey takes us somewhere you might not expect, right here on our own Earth, to places where humans have measured temperatures that would kill unprotected life in minutes, where the air itself would freeze in your lungs. Because before we can understand the cold of space, we need to understand the cold we can touch, measure, and survive. We need to see how our own planet has created frozen laboratories where scientists study the limits of what's possible when heat drains away and stillness approaches. Our home planet holds secrets in its coldest places, temperatures so extreme that exposed skin freezes in under 2 minutes. Places where the air is so cold it would feel like knives in your lungs. Places where thermometers themselves have frozen and shattered. And in these brutal landscapes, scientists have discovered something extraordinary: that Earth itself is a laboratory for understanding cold, a testing ground that teaches us what to expect when we venture beyond our world into the frozen reaches of space. On July 21st, 1983, at a Soviet research station called Vostok in the heart of Antarctica, thermometers recorded something that seemed impossible: minus 89.2 degrees Celsius. That's minus 128.6 degrees Fahrenheit. At that temperature, your breath would freeze into ice crystals before it left your mouth. Any exposed skin would develop frostbite in less than 30 seconds. The moisture in your eyes would begin to freeze. This wasn't just cold, this was a glimpse of what planetary surfaces look like when they exist far from the sun's warmth. And for decades, this stood as the coldest temperature ever naturally recorded on Earth's surface. But Vostok wasn't the end of the story. It was just the beginning, because scientists suspected that Antarctica held places even colder, hidden in regions so remote and hostile that no weather station had ever been placed there. They were right. In August 2010, using satellite data to scan the highest points of the East Antarctic Plateau, researchers discovered something stunning. In shallow depressions near the summit of the ice sheet, where cold, dense air pools and stagnates during the polar winter, temperatures had dropped to minus 93.2 degrees Celsius. That's minus 135.8 degrees Fahrenheit. And these weren't anomalies. These temperatures occurred regularly year after year in multiple locations across the plateau. Think about what that means for a moment. At minus 93 degrees Celsius carbon dioxide, the gas you're exhaling right now would freeze solid. The air itself would begin to condense. You're approaching temperatures where the atmosphere starts to behave differently, where the ordinary rules of weather and climate break down. And this is happening right here on our temperate, life-filled Earth. It's a reminder that our planet contains multitudes that within a few thousand miles you can travel, from tropical rainforests to conditions more extreme than the surface of Mars. But here's what makes these Antarctic cold spots so scientifically valuable: they're natural experiments. By studying how ice behaves at these temperatures, how air moves and settles, how radiation escapes into space on clear polar nights, scientists learn principles that apply throughout the solar system. The same physics that creates these frozen valleys on Earth creates the permanent ice caps on Mars, the nitrogen glaciers on Pluto, the methane lakes on Titan. Antarctica isn't just cold, it's a portal to understanding frozen worlds everywhere. Now, let's talk about why these places get so cold, because the answer reveals something fundamental about how heat moves through the universe. During the Antarctic winter, the sun doesn't rise for months. The continent sits in continuous darkness, tilted away from our star, receiving no solar energy whatsoever. Meanwhile, the ice and snow are excellent radiators. They emit infrared radiation into space extremely efficiently. Heat is constantly leaving, and no heat is coming in. The surface cools, and cools, and cools. The coldest temperatures occur in high-altitude basins, where cold air, which is denser than warm air, flows downhill and pools like water, creating pockets of extreme cold that can persist for days. But Antarctica has competition. In the Northern Hemisphere and Eastern Siberia, there's a region called the Sakha Republic, and within it lies a town with a name that perfectly captures its nature, Oymyakon. In the language of the local Yakut people, it means unfrozen water, referring to a nearby hot spring. The irony is almost poetic, because Oymyakon holds the record for the coldest permanently inhabited place on Earth. In January 1924, a temperature of minus 71.2 degrees Celsius was recorded there. That's minus 96 degrees Fahrenheit. People live there. They raise children there. They go to work, attend school, live ordinary lives in temperatures that would kill an unprepared person in minutes. What does life look like at minus 71 degrees? Car engines must be kept running continuously because if they stop, the oil freezes and the engine becomes a solid block of useless metal. Buildings must be constructed on stilts because the warmth from the structure would melt the permafrost beneath it, causing the building to slowly sink into the ground. Pen ink freezes. Glasses freeze to your face. Batteries die almost instantly. And yet, people endure. They have developed clothing techniques, cultural practices that allow them to survive and even thrive in conditions that seem incompatible with human life. It's a testament to human adaptability, but also a preview of the challenges we'll face if we ever try to colonize cold worlds beyond Earth. Here's a question worth pondering. Why is Vostok colder than Oymyakon, even though Oymyakon is inhabited and Vostok is just a research station? The answer lies in elevation and isolation. Vostok sits at 3,488 meters above sea level on top of an ice sheet that's itself more than 3,700 meters thick. You're standing on ice that's resting on bedrock more than 7 kilometers above the underlying land. At that altitude, the air is thinner, holds less heat, and radiates warmth into space more efficiently. Oymyakon, despite its continental climate and northern location, is at a much lower elevation in a valley where some geographic features provide a tiny amount of shelter from the most extreme conditions. Altitude matters. Geography matters. Every detail of a landscape influences how cold it can become. But Earth's cold isn't limited to land. In the Arctic Ocean, sea ice forms every winter, and the temperature of that ice can drop to minus 40 degrees Celsius or lower. What's fascinating about sea ice is that it's not pure water. It's a matrix of ice crystals with pockets of extremely salty brine trapped between them. As the ice freezes, it excludes salt, concentrating it in these liquid pockets. The brine can remain liquid even at minus 40 degrees because of its high salt concentration. And within these brine channels, incredibly hardy bacteria continue to live, metabolize, and reproduce. They've evolved antifreeze proteins that prevent ice crystals from forming inside their cells. They've developed metabolic pathways that function at temperatures that would stop almost all other life forms. These organisms are teaching us that life's boundaries are far wider than we once believed. This discovery has profound implications for astrobiology. If life can survive in Earth's coldest places in Antarctic ice, in Arctic brine channels and permafrost that's been frozen for millions of years, then perhaps life can survive on Europa Jupiter's moon, with an ocean beneath its ice shell. Perhaps life exists on Enceladus Saturn's tiny moon that spews water into space from cracks in its frozen surface. Perhaps Mars, which once had liquid water and still has ice caps and buried glaciers, harbors dormant life waiting for conditions to improve. Earth's frozen extremes aren't just interesting, they're a blueprint for where to search for life beyond our planet. And then there's our moon. Earth's moon experiences temperature swings that make Antarctic winters seem mild. During the lunar day, which lasts about 2 weeks, surface temperatures in direct sunlight can reach 127 degrees Celsius, hot enough to boil water. But during the lunar night, which also lasts 2 weeks, temperatures plummet to minus 173 degrees Celsius. That's colder than any naturally occurring temperature on Earth's surface. The moon has no atmosphere to retain heat, no ocean to moderate temperature swings, no weather to distribute warmth. It's a dead rock in space, and its temperature is dictated purely by whether the sun is shining on it or not. But here's where it gets truly interesting. At the moon's poles, there are craters so deep that sunlight never reaches their floors. Never. Not for billions of years. These permanently shadowed regions are among the coldest places in the solar system. Temperatures there drop to minus 240 degrees Celsius, just 33 degrees above absolute zero. For comparison, that's colder than Pluto's surface during parts of its orbit. These craters are cold traps, and over billions of years, water molecules that randomly wandered into them became frozen and stuck. NASA's L-Cross mission confirmed in 2009 that these polar craters contain significant amounts of water ice preserved in pristine condition since the early days of the solar system. The moon, our closest cosmic neighbor, contains pockets of cold that rival the most extreme conditions anywhere in our immediate cosmic neighborhood. This is what makes Earth such a valuable teacher. Within one planetary system, Earth, its moon, and the space immediately around them, we can study temperatures ranging from the heat of deserts to cold that approaches the limits of what natural processes can produce. We can watch how ice behaves, how atmospheres respond, how life adapts. Every Antarctic expedition, every Arctic research station, every satellite measuring temperature from orbit is collecting data that will inform our understanding of every cold world we'll ever explore. But perhaps the most important lesson from Earth's frozen places is this cold doesn't mean dead. It doesn't mean sterile. It doesn't mean devoid of interest or beauty or scientific value. Some of the most important research happening on our planet is occurring in its coldest places. Scientists drill ice cores in Antarctica that contain air bubbles from hundreds of thousands of years ago, allowing us to directly measure the composition of Earth's ancient atmosphere. They study how ice sheets flow and crack, helping us predict how climate change will affect sea levels. They discover organisms that thrive in conditions that seem impossible, expanding our understanding of life's resilience. And sometimes in these cold places, we find beauty that takes your breath away. Ice crystals forming intricate fractal patterns. The aurora australis painting the sky above Antarctic research stations with curtains of green and purple light. The strange sculptural shapes of ice formations called penitentes. Tall blades of ice that form in high-altitude snowfields pointing toward the sun like frozen prayers. Cold doesn't have to be barren. Often it creates landscapes and phenomena more striking than anything warm climates can produce. We've measured the coldest places on Earth. We've learned to survive in them, study them, extract their secrets. But our planet, for all its frozen extremes, is still a warm world. It orbits in what astronomers call the habitable zone, the region around a star where liquid water can exist on a planet's surface. Even at minus 93 degrees Celsius, Earth's coldest places are brief anomalies, seasonal extremes that occupy tiny fractions of the planet's surface. The average temperature of Earth is a comfortable 15 degrees Celsius. We live on a warm island in a cold universe. So, what happens when we leave this island? What do we find when we travel to worlds where cold isn't a seasonal extremes but a permanent condition? where entire planets exist at temperatures that would make Vostok seem tropical. That's where our journey takes us now, outward beyond the relative warmth of the inner solar system, to the frozen outer worlds where sunlight is a distant memory and cold reigns eternal across landscapes that challenge everything we thought we knew about planetary science. Beyond the orbit of Mars, past the asteroid belt, past even the massive gas giants Jupiter and Saturn, there exists a realm so cold, so distant from the sun's warmth, that ice becomes rock and gases. We breathe freeze solid. Out here, sunlight arrives 900 times dimmer than it does on Earth. A noonday on these worlds looks like deep twilight. And the cold is so profound that it transforms everything we think we know about how planets should behave. Neptune orbits our sun at a distance of 4.5 billion kilometers. Light from the sun takes over 4 hours to reach it. By the time the light arrives, it's so weak, so diffused by distance, that it provides almost no warmth whatsoever. The cloud tops of Neptune register temperatures around minus 214 degrees Celsius. That's minus 353 degrees Fahrenheit. At those temperatures, methane, a gas on Earth, forms clouds and rains down as ice crystals. The atmosphere isn't made of water vapor like Earth's, but of hydrogen, helium, and methane swirling in storms that rage at speeds up to 2,000 kilometers per hour. Neptune is the windiest planet in our solar system, and scientists still don't fully understand how a world so cold receiving so little energy from the sun can generate such violent atmospheric dynamics. When Voyager 2 flew past Neptune in August 1989, it sent back images that stunned the scientific community. They expected a frozen dormant world, a blue sphere of ice in perpetual stillness. Instead, they found a dynamic atmosphere with a great dark spot, a storm system the size of Earth racing around the planet. They found bright high-altitude clouds of methane ice. They found evidence of internal heat warmth rising from Neptune's core that drives weather patterns in ways we're still working to understand. Neptune taught us that cold doesn't mean inactive. Even at minus 214 degrees, a world can be violently dramatically alive. But Neptune's largest moon, Triton, is where things get truly extraordinary. Triton orbits Neptune backwards retrograde motion, suggesting it wasn't born around Neptune, but was captured possibly from the Kuiper belt beyond. It's one of the coldest solid surfaces we've measured in the solar system, with temperatures hovering around minus 235 degrees Celsius. That's only 38 degrees above absolute zero. Triton's surface is made of frozen nitrogen, frozen methane, frozen carbon dioxide substances that on Earth exist only as gases. And here's what makes Triton remarkable. Despite being colder than almost anywhere else in the solar system, it's geologically active. Voyager 2 observed plumes erupting from Triton's surface, geysers of nitrogen gas carrying dark organic material 8 kilometers into the thin atmosphere. Think about that. At temperatures where almost all molecular motion should cease, Triton is erupting, changing, reshaping its surface. The leading theory is that weak sunlight, even at that distance, penetrates the clear nitrogen ice, creating a greenhouse effect beneath the surface that builds pressure until it explosively vents. Now, let's travel even farther. Out past Neptune lies Pluto. The world that captured imaginations for decades was demoted from planet status, yet proved to be far more complex than anyone anticipated. Pluto orbits at an average distance of 5.9 billion kilometers from the Sun, though its elliptical orbit means that distance varies dramatically. At its coldest, Pluto's surface temperature drops to minus 233 degrees Celsius. The atmosphere, thin as it is made of nitrogen, methane, and carbon monoxide that freeze and fall as snow for part of Pluto's 248-year orbit, then sublimate back into gas as Pluto approaches the Sun. When NASA's New Horizons spacecraft flew past Pluto in July 2015, the images it returned revolutionized our understanding of cold worlds. Scientists expected a cratered dead surface battered by impacts over billions of years. Instead, they found a world of staggering geological diversity. There were mountains made of water. Ice water is rock hard at those temperatures, reaching heights of 3,500 meters. There was Sputnik Planitia, a vast plain of nitrogen ice that appeared to be actively convecting, with warmer ice rising and cooler ice sinking in cells that completely resurfaced the region every 500,000 years. There were features that looked like ice volcanoes, possibly erupting a slurry of water, nitrogen, ammonia, and methane. And perhaps most hauntingly, there was the heart-shaped region that became Pluto's iconic feature, a geological testament to the fact that even at minus 233 degrees, a world can be young, dynamic, and beautiful. But here's something that confuses many people about cold in space, and it's worth clarifying. There's a profound difference between surface temperature and atmospheric temperature on these distant worlds. When we say Pluto's surface is minus 233 degrees, we're talking about the temperature of the ice and rock that makes up the dwarf planet itself. But Pluto also has an atmosphere, and that atmosphere can have different temperatures at different altitudes. In fact, New Horizons discovered that Pluto's upper atmosphere is significantly warmer than expected, around minus 173 degrees Celsius, because it's being heated by solar ultraviolet radiation and by the loss of nitrogen molecules escaping into space. This is one of the beautiful complications of planetary science. Temperature isn't one number. It's a gradient, a profile, a complex interaction between different layers and materials and energy sources. Beyond Pluto lies the Kuiper Belt, a vast ring of icy bodies that extends from about 30 to 50 astronomical units from the Sun. One astronomical unit is the distance from Earth to the Sun. So we're talking about objects orbiting 30 to 50 times farther out than our planet. Out here, temperatures drop even further. The largest known Kuiper Belt object after Pluto is a world called Eris orbiting at an average distance of 68 astronomical units. Eris is covered in methane ice that appears bright white, reflecting most of the feeble sunlight that reaches it. Surface temperatures there are estimated at around minus 243 degrees Celsius. At these temperatures, molecular motion is so slow that surfaces remain almost perfectly preserved for billions of years. Any crater, any geological feature created in Eris's early history is likely still there, frozen in time. And then there's a class of objects that might be the coldest in our solar system, the scattered disk objects and detached objects orbiting in the farthest reaches of the Sun's influence. Objects like Sedna, which has an orbit so elongated that at its farthest point, it reaches 936 astronomical units from the Sun. Out there, the Sun is just another bright star in the sky, providing no more warmth than any other distant point of light. Temperatures in those regions are estimated to drop to around minus 258 degrees Celsius, just 15 degrees above absolute zero. At those temperatures, even helium, which remains liquid down to 4 Kelvin under normal pressure, would freeze solid if there were any atmosphere at all. But there isn't. There's just rock ice and the faint cosmic microwave background radiation, providing the only heat in an otherwise absolute darkness. Now, let's talk about something that surprised scientists when they started studying these cold outer worlds. Many of them have subsurface oceans. Jupiter's moon, Europa, Saturn's moon, Enceladus, and even Pluto might harbor liquid water beneath their frozen shells. How is this possible? If the surface is minus 160 degrees, minus 200 degrees, minus 230 degrees, how can there be liquid water just a few kilometers down? The answer is one of the most important principles in planetary science: tidal heating and radiogenic decay. Europa, for instance, is constantly squeezed and stretched by Jupiter's immense gravity as it orbits. This flexing generates friction, and friction generates enough heat to keep a global ocean liquid beneath an ice shell that might be 10 to 30 kilometers thick. Enceladus is heated by similar tidal forces from Saturn, and larger worlds retain heat from their formation, plus warmth generated by the radioactive decay of elements in their cores. This is where the paradox of cold worlds becomes profound. The coldest surfaces in our solar system may be hiding some of the warmest, most potentially habitable environments. Europa's ocean might contain more liquid water than all of Earth's oceans combined. Enceladus is actively venting water into space through cracks in its south polar ice. NASA's Cassini spacecraft flew through these plumes and detected organic molecules, salts, and evidence of hydrothermal activity. If life needs liquid water, organic chemistry, and energy sources, then these frozen moons might be among the best places to look for life beyond Earth. The cold surface isn't a barrier, it's a protective shell, shielding the ocean beneath from radiation and allowing chemistry to proceed in stable conditions for billions of years. Let me share something that brings this into perspective. In 2005, the Huygens probe carried to Saturn by Cassini descended through the atmosphere of Titan, Saturn's largest moon. Titan's surface temperature is minus 179 degrees Celsius. At those temperatures, water ice is as hard as granite. But Titan has lakes and rivers and rain, not of water, but of liquid methane and ethane. It has weather seasons, erosion, sediment, transport, all the processes that shape Earth's surface, but with different chemistry operating at temperatures where water is rock and methane is liquid. Standing on Titan's surface, you'd see a landscape hauntingly familiar, yet utterly alien hills carved by flowing liquid clouds overhead, rain falling from the sky, pools collecting in valleys. But if you reached down to touch a rock, you'd be touching ice. If you scooped up a handful of soil, you'd be holding fragments of frozen water. The entire geological cycle runs on substances that are gases on Earth. This is what makes the outer solar system so scientifically valuable. It's a laboratory for chemistry under extreme cold. Every reaction, every geological process, every potential pathway to life is slowed down, operating in a regime where quantum effects become more important, and where substances behave in unfamiliar ways. Scientists studying these worlds aren't just cataloging cold places. They're discovering new physics, new chemistry, new possibilities for how matter organizes itself when thermal energy approaches zero. And here's something to consider. We tend to think of cold as inhospitable, but that's a bias from living on a warm world. For chemistry that requires stability, cold is ideal. Complex organic molecules that would break apart at room temperature can persist indefinitely at minus 200 degrees. Chemical reactions that would proceed too rapidly to study on Earth happen slowly enough at low temperatures that every step can be observed. In a very real sense, cold preserves information. It allows complexity to build without thermal chaos tearing it down. Perhaps life didn't begin in a warm pond as Darwin speculated, but in a cold one where molecules had time to find stable configurations before heat could pull them apart. The outer solar system is teaching us to reimagine what habitable means. It's teaching us that cold doesn't mean dead. That distance from the sun doesn't mean absence of energy, and that the most interesting places in our cosmic neighborhood might be the ones where frozen surfaces hide dynamic liquid worlds beneath. Every mission to these distant realms returns data that challenges our assumptions and expands our sense of what's possible. But even these distant worlds, as cold as they are, receive some light from the sun. Faint, yes. Weak beyond measure, yes. But present. What happens when we venture beyond even that faint connection? What do we find in the spaces between stars, where no sun shines, where darkness is absolute, and where cold reaches depths that challenge even our most precise instruments to measure? That's the frontier waiting ahead, the true interstellar cold, where the universe reveals what happens when warmth drains away entirely, and only the faintest whisper of the Big Bang's ancient heat remains. Between the stars, there exists a darkness so complete, a silence so absolute that it defies human comprehension. No planet orbits here, no sun warms the void. The nearest star might be light years away in any direction, its light so faint it would be indistinguishable from thousands of other distant points. And the cold is deeper than anywhere we've discussed so far. This is where the universe shows us what temperature truly means when almost all energy has drained away. Interstellar space. The vast emptiness between star systems has an average temperature of approximately 2.7 Kelvin. That's minus 270.45 degrees Celsius, or minus 454.81 degrees Fahrenheit. We're now just 2.7 degrees above absolute zero, in a realm where the fundamental nature of matter and energy becomes strange, where the rules of everyday physics give way to quantum effects, and where the only source of heat is something extraordinary, the afterglow of creation itself. If this journey through the cosmos is resonating with you, if you're finding peace in understanding these frozen frontiers, take a moment to like this video. And if you haven't joined our community, yet subscribe so we can continue exploring the universe's mysteries together. Your presence here learning and wondering alongside us means everything. That 2.7 Kelvin temperature isn't random. It's not determined by nearby stars or galaxies. It's the temperature of the cosmic microwave background radiation, the oldest light in the universe released approximately 380,000 years after the Big Bang. When the universe was young, it was incredibly hot, filled with a dense plasma of protons, electrons, and photons, all interacting in a brilliant opaque fog. But as the universe expanded, it cooled. Eventually, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. At that moment, photons could finally travel freely through space. The universe became transparent. Those photons have been traveling ever since, and as space itself has expanded, their wavelengths have been stretched redshifted from visible light through infrared and into the microwave portion of the spectrum. Today we detect this radiation coming from every direction in the sky uniform and unchanging, a perfectly preserved snapshot of the universe's childhood. And this ancient light has a temperature 2.7 Kelvin. That's the baseline temperature of the universe itself. No matter where you go in intergalactic space, no matter how far you travel from any source of light or heat, you'll never get colder than 2.7 Kelvin naturally, because this radiation fills all of space. It's the universe's thermostat, the minimum temperature that anything in the natural cosmos can reach just by existing. This is what astronomers mean when they talk about the temperature of empty space, not the absence of heat, but the presence of this ancient cooled remnant of the Big Bang. But here's where the story becomes fascinating. Not all of interstellar space is this cold. In fact, some regions are dramatically colder, while others are surprisingly warm. The interstellar medium, the gas and dust between stars, is remarkably diverse. In regions near hot young stars, ultraviolet radiation heats the gas to temperatures of 10,000 Kelvin or more. In the diffuse ionized gas that fills much of our galaxy, temperatures hover around 8,000 Kelvin. But in the dense molecular clouds where new stars are being born, where gravity is pulling gas together into collapsing clumps, temperatures can drop to just 10 Kelvin. And in the densest, most shielded cores of these clouds, temperatures can fall even lower. These molecular clouds are worth understanding because they're the nurseries of stars, and they're some of the coldest natural environments in the universe. Picture a region of space hundreds of light years across, filled with hydrogen molecules, carbon monoxide, ammonia, water vapor, all frozen or in gaseous form, along with microscopic grains of dust. These clouds are so dense that starlight can't penetrate into their interiors. The dust grains absorb any stray photons and radiate the energy away as infrared light, which escapes into space. Slowly, gradually the cloud cools. In the darkest, most protected regions where no starlight reaches, and where the gas is densest, temperatures can drop to 5 or even 3 Kelvin, just barely above the cosmic microwave background. In these frigid environments, chemistry happens in slow motion. Molecules collide rarely. Reactions that would occur in nanoseconds at room temperature might take years. But given millions of years, complex organic chemistry can still occur. Scientists have detected over 200 different molecules in interstellar space, including amino acids, sugars, and other organic compounds that are the building blocks of life. These molecules form on the surfaces of dust grains, where atoms can stick and slowly migrate until they encounter each other and react. At 10 Kelvin, this process is incredibly slow, but time is something the universe has in abundance. The cold doesn't stop chemistry, it just makes it patient. And then there's the Boomerang Nebula, one of the most extraordinary objects we've ever discovered. Located about 5,000 light-years from Earth in the constellation Centaurus, the Boomerang Nebula is a protoplanetary nebula, a dying star, in the brief phase between being a red giant and becoming a white dwarf. As the star dies, it's ejecting its outer layers into space at a speed of about 164 kilometers per second. This gas is expanding so rapidly that it's cooling through adiabatic expansion, the same principle that makes aerosol cans feel cold when you spray them. The gas is doing work against the vacuum of space, and as it expands, its internal energy drops. Temperature plummets. In the Boomerang Nebula, this expansion has cooled the gas to an astonishing 1 Kelvin, that's minus 272, 15 degrees Celsius, just 1 degree above absolute zero. This is the coldest known place in the natural universe, colder than the cosmic microwave background, colder than the darkest molecular clouds, colder than anywhere else we've measured. For a brief moment, astronomically speaking, this dying star has created a pocket of space colder than the universe itself. Think about what that means. The universe has a natural temperature, the 2.7 Kelvin of the background radiation. To get colder than that, you need an active cooling process, something that removes energy faster than the background radiation can add it. The Boomerang Nebula is losing heat so rapidly through its expansion that it's temporarily beating the universe's thermostat. Eventually, over thousands of years, the expanding gas will thin out, spread across a larger volume, and equilibrate with the background radiation. But right now, in this moment of cosmic time, it's an island of extreme cold in an already cold sea. But here's a question worth pondering: if interstellar space is at 2.7 Kelvin, why don't spacecraft freeze when they travel through it? The Voyager probes, for instance, are now in interstellar space billions of miles from the Sun. Why haven't they frozen solid? The answer reveals something crucial about how heat transfer works in a vacuum. On Earth, we lose heat through 3 mechanisms: conduction, convection, and radiation. Conduction happens when you touch something cold. Heat flows from your warm hand into the cold object through direct contact. Convection happens when air or water carries heat away from your body. But in the vacuum of space, there's no air, no molecules to conduct heat away. The only way to lose heat is through radiation emitting infrared light into space. And that process is slow. Voyager 1 and 2 actually have the opposite problem. They generate heat from their radioactive thermoelectric generators, and they need to radiate that heat away to avoid overheating. The spacecraft are designed with radiators specifically to dump excess heat into space. If they shut down all their systems and stopped generating heat, yes, they would eventually cool to the temperature of the cosmic background. But that would take a very long time, possibly centuries, because radiation is a relatively inefficient way to transfer heat when temperature differences are small. This is an important lesson for understanding cold in space. The vacuum is an excellent insulator. That's why thermoses work. They use vacuum insulation to prevent heat transfer. It's also why astronauts on spacewalks need cooling systems in their suits. They're not at risk of freezing. They're at risk of overheating because their body heat has nowhere to go efficiently. Cold in space doesn't work like cold on Earth. It's not an aggressive stealing presence. It's passive waiting. The real challenge is managing heat in an environment where you can only lose it slowly through radiation. Now, let's talk about what happens to matter at these interstellar temperatures. At 2.7 Kelvin, most substances would be solid. Hydrogen, which makes up most of the universe's normal matter, would be a solid if it existed at typical pressures. Helium, the second most abundant element, would be liquid. It doesn't freeze solid until you get down to about 1 Kelvin, and even then, only under pressure. But in interstellar space, pressures are so low, often just a few atoms per cubic centimeter, that the concepts of solid, liquid, and gas become almost meaningless. Matter exists as isolated atoms or molecules drifting through space, occasionally colliding, but never forming the cohesive materials we're familiar with. There are exceptions, though. Dust grains in interstellar space can accumulate layers of frozen gases on their surfaces. Water, carbon monoxide, methane, ammonia all can condense as ices on these microscopic particles. These icy dust grains are thought to be where much of interstellar chemistry occurs. Two hydrogen atoms might land on the same grain, migrate across its frozen surface until they meet and combine to form molecular hydrogen. Other more complex molecules form through similar processes. The grain acts as a meeting place, a catalyst, and a protective environment where delicate molecules can form without being immediately torn apart by radiation. Scientists have learned an enormous amount about interstellar chemistry by studying the light from distant stars. As starlight passes through intervening clouds of gas and dust, certain wavelengths are absorbed by specific molecules. By analyzing these absorption lines, astronomers can identify what molecules are present and in what quantities. This is how we know that space contains water organic molecules and the chemical ingredients for life. But here's what's remarkable. Many of these molecules only form at very low temperatures. The chemistry of interstellar space is cold chemistry, operating in regimes that we can barely recreate in laboratories on Earth. In 2019, scientists detected helium hydride, the first molecule to form in the universe in the planetary nebula, NG C7027. Helium hydride forms when ionized helium captures an electron and then bonds with hydrogen. In the early universe shortly after the Big Bang, this was the first type of molecular bond to form, as the cosmos cooled enough for chemistry to begin. Finding it in a modern planetary nebula confirmed theories about the chemical evolution of the universe and gave us a direct link to the chemistry of the ancient cosmos. And this molecule, this first chemical bond in the universe's history, requires cool conditions to remain stable. Hot environments would tear it apart. The cold of space preserves it, allows it to exist, and tell its story. Have you ever wondered what it would look like to float in interstellar space? Imagine you're somehow placed there impossibly surviving, protected from the vacuum and radiation. What would you see? The first thing that might surprise you is the darkness. Space is dark not because there's no light, but because there's nothing to scatter light. On Earth, the sky is bright during the day because air molecules scatter sunlight in all directions. In space, without that scattering, the only light you see is light coming directly from its source. Stars would be visible as brilliant, unwavering points, no twinkling, because there's no atmosphere to distort their light. The Milky Way would stretch across the sky as a luminous band of countless distant suns. But between the stars and the vast spaces between those points of light, there would be only blackness, perfect, absolute darkness, and cold. Not the biting cold of a winter wind, but a different kind of cold, the silent, patient cold of emptiness, where heat slowly radiates away and nothing replaces it. This is the frontier that awaits us if we ever truly become an interstellar species. Traveling between stars means spending years, decades, or centuries in this environment. Spacecraft would need to be self-contained ecosystems, maintaining warmth and life in an environment fundamentally hostile to both. They would drift through darkness at speeds we can currently barely imagine, surrounded by cold that reaches back to the beginning of time itself. It's both terrifying and beautiful, a journey into the ultimate wilderness where human ingenuity must overcome the universe's natural tendency toward cold and entropy. But even in this vast, cold emptiness, the universe is still telling stories. Every photon of the cosmic microwave background carries information about the infant universe. Every molecule drifting in interstellar space records the history of stars that lived and died to create it. Every dust grain is an archive of cosmic chemistry. The cold doesn't erase information it preserves, it locks it in place, allows it to persist across billions of years until we develop the tools and knowledge to read what it has to say. Yet there are objects even stranger than empty space worlds that drift through this darkness with no star to call home, rogue planets, and failed stars wandering the galaxy in perpetual isolation. These are objects that have known warmth or that almost achieved it, but now exist in temperatures that make even interstellar space seem warm by comparison. They are the outcasts of the cosmos, and their stories reveal yet another dimension of what cold means when you venture beyond the comfort of stellar light. Imagine a world that has never seen a sunrise, a planet that was born in a solar system, orbited a star for perhaps millions of years, and then was violently ejected into the darkness cast out by gravitational interactions with other planets or passing stars. Now it drifts alone through the galaxy, traveling through interstellar space with no light to warm it, no day or night cycle, no seasons, just eternal darkness and cold that deepens with every passing million years. These rogue planets exist. Billions of them may be wandering our galaxy right now, invisible and alone. Astronomers estimate there could be more rogue planets in the Milky Way than there are stars. Think about that for a moment. Our galaxy contains somewhere between 100 and 400 billion stars, and there might be even more planets drifting in the spaces between them, orphaned worlds that once knew the warmth of a sun, but now exist in temperatures approaching absolute zero. Most of these rogue planets are completely dark. They emit no visible light, only faint infrared radiation from the residual heat of their formation. Detecting them is extraordinarily difficult. They're like finding a coal nugget in a dark room from miles away. If you're captivated by these lonely wanderers, these worlds adrift in cosmic night, show your support by liking this video. And subscribe to join us as we continue exploring the universe's most profound mysteries. Every subscription helps us create more content like this, and we're grateful for each and every one of you. The first confirmed detection of a rogue planet came in 2000 when astronomers discovered an object designated as S-Ori 70 in the Sigma Orionis cluster. It had a mass about 3 to 10 times that of Jupiter, but it wasn't orbiting any star. It was just there floating through space. Since then, we've confirmed dozens more, and gravitational microlensing surveys suggest there are countless others too dim and distant to detect with current technology. These surveys work by watching for the brief brightening of a distant star. When an invisible object passes in front of it, the rogue planet's gravity bends and magnifies the star's light for a few hours or days, giving away its presence. Now, here's what makes rogue planets so fascinating from a temperature perspective. Without a star, their only sources of heat are internal. When a planet forms, it's hot from the energy of colliding material. Larger planets retain this formation heat for billions of years. Jupiter, for instance, radiates about twice as much energy into space as it receives from the Sun, because its interior is still slowly cooling from its formation 4.6 billion years ago. But a rogue planet cut off from stellar radiation cools much faster. Within a few tens of millions of years, a Jupiter-sized rogue planet's surface temperature would drop to around 50 Kelvin, minus 223 degrees Celsius. That's colder than any planetary surface in our solar system. But could life exist on a rogue planet? At first, the answer seems obviously no. Without sunlight, there's no energy for photosynthesis, no warmth for liquid water on the surface, no day and night to drive atmospheric circulation. But here's where it gets interesting. Underneath the surface, conditions might be very different. If a rogue planet is large enough, or if it has a large moon creating tidal heating, or if it has a thick hydrogen atmosphere that acts as an insulating blanket, It could maintain liquid water in a subsurface ocean for billions of years. The heat from radioactive decay in the planet's core, combined with residual formation, heat, and tidal forces, could keep water liquid even as the surface remains frozen at temperatures near absolute zero. In 2011, planetary scientists published calculations showing that a rogue planet with a thick hydrogen atmosphere could maintain surface temperatures above the freezing point of water indefinitely. The hydrogen atmosphere would act like an extreme greenhouse trapping infrared radiation emitted by the planet's interior. Such a world might have lakes, rivers, even rain, all existing in perpetual darkness, lit only by volcanic activity or bioluminescence if life evolved there. It's speculative, but it's also physically possible. The universe might contain billions of these dark habitable worlds, thriving ecosystems that evolve without ever seeing a star. Now, let's talk about brown dwarfs, objects that occupy a strange middle ground between planets and stars. A brown dwarf forms like a star from a collapsing cloud of gas, but it never accumulates enough mass to ignite sustained hydrogen fusion in its core. Stars need at least about 75 times Jupiter's mass to achieve the temperatures and pressures required for fusion. Brown dwarfs have between 13 and 75 Jupiter masses too big to be planets, too small to be stars. They're failed stars, objects that glow dimly from the heat of their formation and from the fusion of deuterium, a heavy isotope of hydrogen, but they gradually cool over billions of years. The coolest brown dwarfs we've discovered challenge our understanding of what these objects can be. In 2014, astronomers using the Wide Field Infrared Survey Explorer, WISE, discovered an object designated WISE 0855-0714, located just 7.2 light-years from Earth. This brown dwarf has a temperature estimated at -48 to -13 degrees Celsius. Let me repeat that: -48 to -13 degrees Celsius. That's colder than the winter temperatures in many places on Earth. This object is not hot by any definition we normally apply to celestial bodies. It's cold, freezing cold. If you could somehow stand on its surface, and you couldn't, because it's a gas giant without a solid surface, the temperature would be comparable to a harsh winter day in Antarctica. WISE 0855-0714 is so cold that water vapor condenses in its atmosphere, forming clouds. Water clouds, just like on Earth. This brown dwarf has weather patterns driven by water condensation and evaporation, the same processes that create rain and snow on our planet. Spectroscopic observations have confirmed the presence of water absorption, features in its atmosphere, along with signatures that might indicate sulfur compounds. It's a bizarre hybrid, an object with planetary temperatures, but stellar formation and mechanisms, a world that defies easy categorization. The discovery of objects like WISE 0855-0714 has forced astronomers to reconsider the boundary between planets and brown dwarfs. If a brown dwarf can be as cold as a winter day on Earth, and if a rogue planet can be as large as several Jupiter masses, then what's the actual difference? The answer increasingly seems to be formation and mechanism rather than temperature or size. Brown dwarfs form from collapsing gas clouds like stars. Planets form in disks around stars and might later be ejected, but an object floating alone in space with a temperature of -40 degrees could be either one, depending on how it formed, and from a distance we often can't tell. The coldest brown dwarfs belong to a spectral class called Y dwarfs. These are the coolest, dimmest, stellar-type objects known. Their atmospheres contain methane, ammonia, water, and possibly other compounds that condense into clouds at low temperatures. Some Y dwarfs might have atmospheric temperatures as low as 300 Kelvin, about 27 degrees Celsius. That's warmer than room temperature. An object that formed like a star, glowing with its own internal heat, but with a surface temperature comfortable enough for humans to tolerate if we could somehow stand there. It reshapes our mental image of what stellar objects look like. Here's something most people don't realize. Brown dwarfs continue to cool throughout their existence, and they cool predictably. A brown dwarf's temperature tells you its age and mass. Young brown dwarfs can be as hot as 2000 Kelvin, hot enough to glow visibly red. But over tens of millions of years, they radiate their heat into space and cool. Eventually, all brown dwarfs will become white dwarfs, and eventually, over trillions of years, they'll cool to the temperature of the cosmic microwave background. They'll become invisible dark objects, indistinguishable from rogue planets except by their composition and formation history. The universe will be filled with these ghosts objects that once glowed with their own light, now cold and dark, drifting through space. But even as they cool, brown dwarfs and rogue planets remain geologically active inside. Jupiter, as we mentioned, still radiates more heat than it receives. Its interior is alive with convection currents, with layers of metallic hydrogen generating powerful magnetic fields. The same processes occur in brown dwarfs, and probably in the larger rogue planets. These objects might have auroras dancing in their atmospheres, powered by interactions between their magnetic fields and charged particles. They might have lightning storms driven by atmospheric convection. They exist in the dark, yes, but they're not dead. They're worlds unto themselves, with weather geology and physics all operating in the absence of a parent star. In 2017, astronomers discovered a brown dwarf called SIMP J 0136663 plus 0933473. A mouthful of a designation that has a magnetic field 200 times stronger than Jupiter's. This magnetic field is so powerful that it accelerates electrons to high energies, producing radio emissions we can detect from Earth. The brown dwarf essentially broadcasts its presence across interstellar space through radio waves. It's a lighthouse in the dark, powered entirely by internal processes with no star needed. Observations revealed that this object also has auroral activity like the northern lights on Earth, but on a scale thousands of times larger, flickering across an atmosphere with no sun to illuminate it. Can you imagine standing on a moon, orbiting a rogue planet or brown dwarf? The primary world would fill the sky, but it wouldn't be bright, like Jupiter seen from Europa or Saturn seen from Titan. It would be dark, visible only as a black circle blocking the stars, perhaps ringed with faint auroras or glowing dimly in infrared wavelengths your eyes couldn't detect. The sky would be filled with stars, more stars than you can see from Earth, because there's no light pollution, no atmosphere scattering light, just the pure darkness of space and the countless points of distant suns. But there would be no warmth from those stars, no seasons, no cycles, just cold deepening slowly over geological time, as the world beneath your feet radiates its remaining heat into the void. These wandering worlds also raise profound questions about panspermia, the idea that life might spread between star systems. If a planet with life is ejected from its solar system, could organisms survive in the deep ice and subsurface oceans, waiting for the rare chance encounter when the rogue planet passes through another star system and is temporarily warmed? Could life evolve on a rogue planet in eternal darkness using chemosynthesis, chemical energy from volcanic vents instead of photosynthesis? If life is truly resilient, truly adaptable, then these dark worlds might be habitable after all. Not in the way we normally think of habitability, but in ways we're only beginning to imagine. Some scientists have proposed that rogue planets might even be preferable for advanced civilizations, without the radiation from a star, without stellar flares or eventual stellar death. To worry about a rogue planet with sufficient internal heat could be a stable home for billions of years. A civilization on such a world would need to master fusion or other energy sources. But once they did, they'd have a stable platform in a quiet, radiation-free environment. They could travel the galaxy along with their planet, a generation ship of continental scale, taking millions of years to drift between star systems, but carrying an entire biosphere with them. The more we learn about these objects, the more we realize that the universe's inventory of cold worlds vastly exceeds what we once thought possible. We used to think of planets as things that orbit stars. Now we know that planets or planet-like objects can exist anywhere, drifting freely, cooling slowly, perhaps harboring life in ways that don't require sunlight. Brown dwarfs blur the line between planet and star, showing us that the cosmos doesn't fit neatly into our categories. There's a continuum of objects from the hottest stars to the coldest rogue planets. And somewhere in that continuum are worlds with temperatures, compositions, and conditions we're only beginning to explore. These frozen wanderers remind us that coldness and isolation don't necessarily mean death or emptiness. Even in the darkest reaches of the galaxy, even on worlds that have been cast out from their home, systems processes continue. Magnetic fields generate, atmospheres swirl, heat flows from deep interiors toward cold surfaces. And perhaps in some cases, life finds a way. The universe is teaching us that habitability isn't about being in a star's Goldilocks zone. It's about having the right combination of energy, chemistry, and time. And those combinations might exist in places we never thought to look. But there's one more frontier to explore in our understanding of cold, one more realm where temperature approaches its absolute limit, and where matter begins to behave in ways that seem to violate common sense. To understand the coldest possible states of existence, we need to descend even further, not into space, but into the quantum realm where scientists have pushed temperatures lower than anything nature has produced, creating conditions where atoms lose their individual identities and merge into states of matter that sound like science fiction but are beautifully, impossibly real. In laboratories around the world, scientists have achieved something that doesn't exist anywhere in the natural universe. They've created temperatures lower than the coldest nebula, colder than interstellar space, colder than anything the cosmos has produced in 13.8 billion years. They've cooled atoms to billionths of a degree above absolute zero. And at these temperatures, matter stops behaving like matter. It transforms into something else, entirely states of existence, where the laws of quantum mechanics, usually hidden at the atomic scale, become visible to the naked eye. At 50 nanokelvin, that's 0.000000005 degrees above absolute zero, atoms stop acting like individual particles. They merge, they overlap. They become a single quantum entity called a Bose-Einstein condensate, where thousands or millions of atoms occupy the same quantum state, think the same quantum thoughts, and move as one unified wave. It's matter behaving like light. It's the boundary between the world of particles and the world of waves dissolving completely. And it only happens at temperatures so cold that achieving them requires some of the most sophisticated technology humanity has ever created. If this glimpse into the quantum frontier fascinates you, if you want to see just how strange physics becomes, when we push temperature to its limits, go ahead and hit that like button. And subscribe to stay with us through this journey. We're exploring ideas that reshape everything we thought we knew about how the universe works at its most fundamental level. Let's start with superconductivity, because it was the first quantum phenomenon that scientists observed at extremely low temperatures, and it changed physics forever. In 1911, Dutch physicist Heike Kamerlingh Onnes was studying the electrical properties of mercury at low temperatures. He'd recently succeeded in liquefying helium, which boils at just 4.2 Kelvin, giving him access to the coldest sustained temperatures ever achieved in a laboratory when he cooled mercury to 4.2 Kelvin. Something shocking happened. Its electrical resistance vanished completely. Not became very low, actually dropped to zero. He could start a current flowing through a loop of superconducting mercury, disconnect the power source, and the current would continue flowing indefinitely with no loss of energy, no heat generation, no degradation whatsoever. This wasn't just an incremental discovery. It violated everything physicists understood about how materials conduct electricity. In normal conductors, Electrons collide with atoms as they flow through the material, creating resistance and generating heat. That's why your phone charger gets warm. Energy is being lost to resistance. But in a superconductor, electrons pair up in a quantum dance called Cooper pairs. And these pairs move through the material without any friction at all. They flow as a single quantum state, coordinated across the entire sample. It's as if millions of dancers suddenly synchronized perfectly, moving through a crowded room without ever bumping into anyone. Today, superconductors are crucial for technology. MRI machines use superconducting magnets cooled with liquid helium to generate the powerful magnetic fields needed for medical imaging. The Large Hadron Collider uses superconducting magnets to steer protons around its 27-kilometer ring. Experimental fusion reactors use superconducting coils to contain plasma at 150 million degrees, using extreme cold to control extreme heat. But here's what's frustrating. Most superconductors only work at temperatures below about 30 Kelvin. You need liquid helium, expensive cooling systems, and constant maintenance. Scientists have discovered high-temperature superconductors that work up to about 138 Kelvin, still far below room temperature. But we don't fully understand how they work. Room temperature superconductivity remains one of the holy grails of physics, a discovery that would revolutionize energy transmission, transportation, and computing. Now, let's talk about superfluidity, which is even stranger than superconductivity. Cool liquid helium to about 2.17 Kelvin called the lambda point, and it undergoes a phase transition into something called helium-2, or a superfluid. And the behavior is absolutely bizarre. A superfluid has zero viscosity, no internal friction. If you stir a superfluid in a container, it will continue spinning forever. Put it in a beaker, and it will creep up the walls, flow over the edge, and drip down the outside all on its own, driven by quantum effects. It's perpetual motion, not because energy is being created, but because no energy is being lost to friction. In 1938, Russian physicist Pyotr Kapitsa discovered superfluidity, and his experiments revealed properties that seemed impossible. Superfluids flow through tiny cracks and pores that would stop any normal liquid. They conduct heat hundreds of times better than copper. If you try to rotate a container of superfluid, the fluid doesn't rotate with it, only the container spins, while the superfluid inside remains stationary. This violates our intuitive understanding of fluids. Imagine stirring a cup of coffee and having the coffee refuse to spin with the spoon. That's what superfluids do, because they're not really fluids. In the normal sense, they're macroscopic quantum objects. The explanation involves quantum mechanics. At normal temperatures, helium atoms are individuals, each with its own quantum state bouncing around chaotically. But as you cool helium toward absolute zero, something remarkable happens. Helium atoms are bosons particles that can occupy the same quantum state. Below the lambda point, a significant fraction of the helium atoms condense into the same quantum ground state, the lowest energy configuration available. They stop being individual atoms and become a single quantum entity. When a large number of atoms share one quantum state, they move in perfect coordination. There's no friction because friction requires individual particles colliding and exchanging energy randomly, and these atoms aren't individuals anymore. They're a coherent quantum system. This brings us to Bose-Einstein condensates, which are to superfluids what superfluids are to ordinary matter, an even more extreme manifestation of quantum behavior. The theoretical foundation was laid in 1924 by Satyendra Nath Bose and Albert Einstein. Bose was studying the statistical properties of photons, particles of light, and derived a new way of counting quantum states. Einstein realized that Bose's mathematics could apply to atoms too, and he predicted that if you cooled a gas of bosonic atoms to temperatures near absolute zero, they would all condense into the same quantum state. The gas would become a single quantum entity. For decades, this remained theoretical. No laboratory could reach temperatures low enough. In 1995, after years of development in cooling techniques, three groups of scientists, Eric Cornell and Carl Wieman at the University of Colorado, and Wolfgang Ketterle at MIT, finally achieved it. Using laser cooling and magnetic traps, they cooled rubidium and sodium atoms to temperatures below 1 microkelvin, 1/1,000,000th of a degree above absolute zero. The atoms condensed into a Bose-Einstein condensate, and the scientists watched as a cloud of individual atoms transformed into a single quantum object. They could see the wave nature of matter with their eyes. Atoms, which we usually think of as particles, were behaving like a single coherent wave, just like Einstein predicted 70 years earlier. Cornell, Wieman, and Ketterle won the Nobel Prize in Physics in 2001. What does a Bose-Einstein condensate look like? Imagine you're watching a crowd of people at a concert. Everyone is moving independently, dancing to their own rhythm. That's atoms at normal temperatures. Now imagine the music stops, and suddenly everyone freezes in perfect synchronization, moving as one coordinated unit. That's a Bose-Einstein condensate. The atoms lose their individual identities. They overlap in space. They share the same quantum wave function. If you measure one atom's properties, you've measured them all because they're all in the same state. It's matter at its most quantum, where the distinction between particle and wave completely breaks down. Since 1995, scientists have created Bose-Einstein condensates from dozens of different elements and explored their properties. These condensates can be manipulated with lasers shaped into different geometries, made to flow and interfere with each other. They're being used to create the most precise atomic clocks ever built, devices that won't gain or lose a second in 15 billion years. They're being studied as analogs for cosmological phenomena. The way sound waves propagate through a condensate resembles how light behaves near black holes. They're tools for exploring quantum mechanics at scales large enough to see and manipulate. But here's what truly captures the imagination. Bose-Einstein condensates exist in a regime where quantum mechanics and everyday reality overlap. Normally, quantum effects are confined to atoms and subatomic particles. You can't see quantum superposition or entanglement with your naked eye. But a Bose-Einstein condensate is a quantum object that's millimeters across, containing trillions of atoms all occupying a single quantum state. It's quantum mechanics made visible. It's proof that the strange counterintuitive rules governing the atomic world don't disappear at larger scales. They're just harder to see, because thermal energy usually masks them. In 2003, scientists created something even more exotic, a fermionic condensate. Remember, particles come in two types: bosons, which can share quantum states, and fermions, which can't. Each fermion must occupy its own unique quantum state. Electrons are fermions. Protons and neutrons are fermions. You're made of fermions. The Pauli exclusion principle, which says no two fermions can share the same quantum state, is why matter has solidity, why you don't fall through your chair. But at temperatures below 1 microkelvin, fermionic atoms can pair up, and these pairs behave like bosons. The fermions form Cooper pairs, just like in superconductors, and the pairs can then condense into a single quantum state. You get a superfluid made of fermions, something that shouldn't be possible by ordinary rules, but emerges from quantum mechanics at ultra-low temperatures. Now, let's talk about how scientists actually achieve these temperatures, because the techniques are as remarkable as the phenomena they reveal. You can't just put atoms in a freezer. You can't surround them with something colder, because there isn't anything colder. Instead, scientists use a process called laser cooling. Here's how it works. Imagine an atom moving toward you. It's moving because it has kinetic energy. It's warm. You shine a laser at it, tuned to a specific frequency that the atom can absorb. When the atom absorbs the photon, it gains momentum in the direction opposite to its motion. The photon acts like a tiny brake, slowing the atom down. The atom then re-emits the photon in a random direction. Repeat this process millions of times, with lasers shining from multiple directions. and you can slow atoms down to just centimeters per second. Since temperature is just average kinetic energy, slowing atoms means cooling them. Laser cooling can reach temperatures around 1 millikelvin, 1,000th of a degree above absolute zero. But that's not cold enough for Bose-Einstein condensation. The final step is evaporative cooling. Scientists trap the coldest atoms in a magnetic field, then gradually weaken the trap, allowing the hottest atoms, the ones with the most energy, to escape. It's like blowing on hot soup. You're removing the hottest molecules, and the average temperature of what remains drops. Through careful evaporation, scientists can cool atoms from 1 millikelvin to 50 nanokelvin, or even lower. In 2003, researchers at MIT achieved a temperature of 450 picokelvin, that's 0.00000000045 degrees above absolute zero. At that temperature, atoms are moving at just half a millimeter per second. They're almost perfectly still. Why go to such extremes? Because this is where the universe reveals secrets it keeps hidden everywhere else. At ultra-low temperatures, quantum effects dominate. Scientists can study how atoms interact at the quantum level, test fundamental theories of physics, and explore states of matter that don't exist naturally anywhere in the cosmos. These experiments are windows into the quantum foundations of reality itself. They're showing us that the universe isn't made of tiny billiard balls bouncing around. It's made of wave functions, probability fields, quantum states that we're only beginning to understand. There's also a practical side. Quantum computers rely on maintaining quantum coherence, keeping quantum bits in superposition, states long enough to perform calculations. Temperature is the enemy of coherence because heat causes random fluctuations that destroy delicate quantum states. By understanding how matter behaves at nanokelvin, temperature scientists are developing better techniques for quantum computing, quantum sensing, and quantum communication. The coldest temperatures ever achieved aren't just curiosities, they're the foundation for technologies that might define the next century. And here's something profound: by creating temperatures lower than anything in the natural universe, we've expanded the universe's own experience of itself. For 13.8 billion years, the cosmos never knew what matter looks like at 50 nanokelvin. It never experienced Bose-Einstein condensation on the scales we've created it. Then humans came along with our curiosity and our technology, and we showed the universe something new. We created conditions that didn't exist, revealed phenomena that were always possible but never actualized. In a very real sense, we've enriched the cosmos, added new chapters to its story. But as we push temperature lower and lower, approaching but never reaching absolute zero, we're confronting a fundamental limit built into the fabric of reality itself. The third law of thermodynamics tells us that absolute zero cannot be reached by any finite number of steps. Quantum mechanics tells us that even at zero temperature, particles must retain a minimum energy called zero-point energy. They can never be completely at rest. These aren't technological limitations. They're laws of nature, boundaries written into the mathematics of existence. This raises profound questions that extend beyond temperature and touch on the ultimate fate of everything. If the universe continues expanding and cooling, if stars eventually die and galaxies drift apart, what happens when the cosmos itself approaches absolute zero? When all energy has been radiated away, all matter has decayed, and nothing remains but a cold, dark void. That's the scenario we need to explore next. Not just the cold of a laboratory or a distant nebula, but the cold at the end of time, when the universe reaches its ultimate thermal equilibrium and faces what physicists call the heat death. It's a vision both unsettling and strangely beautiful, a reminder that everything warm, everything bright, everything we cherish exists in a brief window before the long, final cold. Trillions of years from now, when the last star has burned out, when every black hole has evaporated, when every particle has drifted so far from every other particle that the universe is essentially empty, what will the temperature be? The answer is both simple and haunting nearly 0 Kelvin. The universe is slowly, inexorably cooling, moving toward a state of maximum entropy, where all differences in temperature, all gradients of energy, all possibilities for change will have disappeared. This is called the heat death of the universe, and it represents the ultimate expression of cold, not just the absence of warmth, but the end of time itself. The concept sounds like something from science fiction, a dystopian vision of cosmic doom, but it's rooted in one of the most fundamental principles of physics, the second law of thermodynamics. This law states that entropy, roughly speaking, disorder, or randomness always increases in a closed system. You can create pockets of order temporarily, like building a sandcastle or organizing your room, but only by increasing disorder somewhere else. The universe as a whole is a closed system, and its total entropy has been increasing since the Big Bang. Eventually, entropy will reach its maximum possible value, and when that happens, nothing can change anymore. The universe will have reached thermal equilibrium, at a temperature just above absolute zero. If contemplating the far future gives you a sense of perspective, if thinking about the ultimate fate of everything helps you appreciate the warmth and light we have, now show your appreciation by liking this video. And subscribe to continue this journey with us through the deepest questions science can ask. Let's trace the timeline of cosmic cooling, because understanding how we get from here to heat death reveals something profound about the nature of time and energy. Right now, the universe is 13.8 billion years old. It's filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. Stars are fusion reactors converting hydrogen into helium, and heavier elements pouring energy into space in the form of light and heat. This process can't continue forever. Every star has a finite fuel supply. Small stars, red dwarfs, with masses around 10%, that of our sun, can burn for 10 trillion years. But they will eventually run out of fuel, cool and fade to black dwarfs, stellar corpses that no longer generate heat. By about 100 trillion years from now, the last conventional stars will have died. The universe will enter what cosmologists call the degenerate era. During the degenerate era, the primary objects in the universe will be white dwarfs, neutron stars, and black holes. White dwarfs are the remnants of stars. Like our sun, their nuclear fusion has stopped, and they're slowly radiating away their residual heat. A white dwarf starts its existence at temperatures around 100,000 Kelvin, glowing white hot. But over billions of years, it cools. After about 10 to the power of 15 years, that's a quadrillion years, white dwarfs will have cooled to around 5 Kelvin, barely warmer than the cosmic microwave background. Eventually, they'll become black dwarfs, theoretical objects that have cooled to the temperature of their surroundings, no longer emitting any detectable light or heat. Here's something most people don't realize: black dwarfs don't exist yet. The universe isn't old enough for any white dwarf to have cooled completely. The coolest white dwarfs we've observed are still thousands of degrees. Black dwarfs are predictions objects that will only exist in the far future, when the universe has had time to cool them completely. They'll be invisible, detectable only through their gravitational influence, dark, dense spheres drifting through an even darker cosmos. But white dwarfs aren't stable forever. Quantum mechanics predicts a process called proton decay. The idea that even protons, which we normally think of as stable, will eventually decay into lighter particles. The predicted timescale is around 10 to the power of 34 to 10 to the power of 36 years, though this has never been observed and remains theoretical. If proton decay occurs, then by 10 to the power of 40 years from now, all ordinary matter, every atom, every molecule, everything made of protons and neutrons will have disintegrated. White dwarfs, neutron stars, even the cold dead planets floating through space will dissolve into radiation and subatomic particles. The universe will enter the black hole era, when the only significant gravitating objects remaining are black holes. Black holes seem like they should be eternal, but Stephen Hawking discovered in 1974 that they're not. Due to quantum effects near the event horizon, black holes emit radiation now called Hawking radiation and slowly lose mass. The rate of this evaporation depends on the black hole's size. Small black holes evaporate quickly. Massive ones take incomprehensibly long. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate. A supermassive black hole, billions of times the Sun's mass, would last until about 10 to the power of 100 years. But eventually, even the largest black holes will evaporate, converting all their mass into radiation that disperses into space. And then, what after 10 to the power of 100 years, the universe enters what's called the dark era. No stars, no planets, no black holes. Just a thin soup of photons, neutrinos, electrons, and positrons, all drifting through an expanding cosmos. The temperature approaches the lowest possible value allowed by the expansion of space itself. If the universe continues expanding, and all evidence suggests this temperature will asymptotically approach absolute zero, but never quite reach it. The universe becomes a cold, dark, nearly empty void, with particles so diluted that they might travel for trillions of light years without encountering anything else. This is heat death. Not a dramatic explosion or collapse, but a slow fade to nothing. All energy differences have been erased. All matter has decayed or dispersed. The universe has reached maximum entropy, a state of perfect uniformity where nothing can happen because there are no gradients left to drive any process. Time in any meaningful sense stops, not because time itself ceases to exist, but because there are no changes left to measure. Clocks require energy differences to tick. Thoughts require chemical gradients to fire. Life requires metabolism, which requires consuming energy and expelling waste heat. In a universe at thermal equilibrium, none of these things are possible. Now here's where it gets philosophically profound. Does time have meaning in a universe where nothing changes? Physicists debate this question. Time as we experience it is intimately connected to causality, to the flow from past to future, to the increase of entropy. The arrow of time points in the direction of increasing entropy, but at maximum entropy, there is no arrow. Past and future become indistinguishable. Some physicists argue that time effectively ends at heat death, not because the parameter we call time stops, but because it becomes irrelevant. Nothing marks its passage. The universe exists in a state of eternal unchanging now. But here's a twist. There are other possibilities. Heat death assumes the universe will expand forever at an accelerating rate driven by dark energy. And current observations support this. Distant galaxies are accelerating away from us, and the universe seems destined for endless expansion. But we don't fully understand dark energy. If its properties change over cosmic timescales, other fates become possible. One alternative is the Big Rip, where dark energy strengthens until it tears apart galaxies, then stars, then planets, then molecules, then atoms themselves. The universe would end not in cold, but in fragmentation, with even the fabric of space-time shredding. Another possibility is the Big Crunch, where the expansion reverses and the universe collapses back into a hot, dense state, the opposite of heat death, ending in infinite heat rather than cold. There's also the possibility of vacuum decay. Our universe might exist in what's called a false vacuum, a stable state, but not the lowest possible energy state. Quantum mechanics allows for the possibility that somewhere at some time, a true vacuum bubble could form and expand at the speed of light, converting the false vacuum into the true vacuum. The laws of physics inside this bubble might be completely different. All matter would be restructured. The universe as we know it would cease to exist, replaced by something fundamentally different. This could happen tomorrow or never, or in 10 to the power of 500 years. We have no way of predicting it or preventing it. But let's return to heat death, because it's the most likely scenario given our current understanding. What's remarkable is that heat death isn't about destruction, it's about equilibrium. Energy is conserved, nothing is lost. but it's all spread out so uniformly diluted across such vast distances that it can no longer do anything useful. Imagine taking a cup of hot coffee and pouring it into an ocean. The energy is still there. The ocean's temperature increases by an infinitesimally tiny amount, but the coffee's warmth is gone, dissolved into an environment so large that it makes no meaningful difference. That's what happens to all the energy in the universe. Every photon emitted by every star, every bit of heat from every living creature, every explosion, and every whisper of motion, all of it eventually spreads out, redshifts away, becomes undetectable. The universe doesn't run out of energy. It runs out of useful energy, concentrated enough to drive processes to create gradients to allow change. Here's something to ponder. If you could somehow survive until the heat death of the universe, obviously impossible. But bear with me, what would you experience? You'd be in a universe at a uniform temperature of nearly absolute zero. No stars visible because they all burned out trillions of years ago. No galaxies because they've all dispersed or collapsed into black holes that subsequently evaporated. The cosmic microwave background radiation, which currently fills space at 2.7 Kelvin, would have redshifted into longer and longer wavelengths, its temperature dropping as the universe expanded. Eventually, its temperature would be 10 to the power of minus 30 Kelvin or lower, so close to absolute zero that the difference is academically irrelevant. You'd be floating in absolute darkness, absolute silence, absolute cold. No reference points, no changes, no time in any practical sense. It sounds bleak, and it is. But here's the curious thing. From a certain perspective, heat death is just the universe achieving perfect balance. All debts paid, all accounts settled, all differences resolved. It's the ultimate expression of fairness. No region of space has more energy than any other. No particle has an advantage, no structure persists through inequality. It's cold, yes, but it's also peaceful. A cosmic rest after the frenetic activity of the first 100 trillion years. And there's beauty in knowing that we live in the opposite of heat death. We exist in an era of the universe when entropy is still relatively low, when energy is concentrated into stars and galaxies, when gradients exist that allow for complexity, life, and thought. Every moment of warmth, every experience of light, every connection between living beings is borrowed from this temporary state of disequilibrium. We're surfing a wave of entropy, riding the transition from order to disorder, and that transition is what makes existence possible. Some physicists have speculated about whether new universes could be born from a heat-death state. Quantum fluctuations might create tiny bubbles of low entropy that expand into new cosmos with their own laws of physics. In this view, our universe's heat death might be the birth of countless other universes, a cosmic reproduction on timescales so vast they dwarf the entire history of our current cosmos. It's speculative, untestable with current technology, but it's a reminder that even endings might be beginnings in disguise. There's also the anthropic principle to consider. We find ourselves living in an era of the universe when stars shine and life is possible, because those are the only eras when observers like us can exist. In the heat-death universe, there are no observers, no questions being asked, no one to care that the cosmos has grown cold. The universe's story is only being told now in this brief cosmic moment when complexity and consciousness have emerged. After heat death, the story ends not because the universe ceases to exist, but because there's no one left to tell it or hear it. So, what do we take from this vision of ultimate cold? What does it mean for us living our brief lives on this small planet orbiting an average star in an unremarkable galaxy? Perhaps it's a reminder of how precious warmth is, how improbable, how temporary. The difference in temperature between your body and the environment isn't just a physical fact, it's what allows you to be alive, to think, to feel, to experience anything at all. That warmth comes from the sun and ultimately from the Big Bang, and it's slowly radiating away into space, never to return in quite the same form. But we still have time. Trillions of years. The sun will shine for another 5 billion years before expanding into a red giant. Humanity, if we survive, has eons ahead to explore, create, and experience. The heat death is so far in the future that it might as well be infinite. By the time it arrives, the universe will have had opportunities for complexity and life that we can barely imagine. Perhaps civilizations will arise that learn to harvest energy from black holes, postponing heat death for themselves. Perhaps consciousness will find ways to persist even in the cooling cosmos, slowing its metabolism to match the universe's declining temperature, thinking one thought every trillion years. Or perhaps heat death is simply the end, and the universe's brief moment of warmth and light is all there is. Either way, we're here now. We're experiencing the universe at its most vibrant, most energetic, most alive. And that realization that we exist in this golden era before the long cold might be the most profound gift cosmology can give us. It teaches us to appreciate warmth, to cherish light, to value the fleeting moments of complexity in a cosmos that tends inexorably toward simplicity. Having seen where the universe is going toward cold, toward equilibrium, toward an ending, both peaceful and absolute, we're ready to bring our journey home back to this moment, this place, this brief flicker of warmth in the cosmic dark. Because understanding the coldest places in the universe, from Antarctic ice to the far future, ultimately helps us understand what warmth means, why it matters, and how achingly beautiful it is that we're here to feel it at all. We've traveled far together from Antarctic ice to the edges of reality itself, from quantum laboratories to the end of time. We've explored places so cold, they make winter seem tropical temperatures so low that atoms stop moving and matter forgets how to be solid. But now, having witnessed the universe's capacity for cold, for stillness, for the slow fade toward absolute zero, it's time to turn our attention back to warmth. Back to the improbable miracle of heat in a cosmos that wants everything to cool down. Because here's what our journey reveals. Warmth is rebellion. Every warm thing in the universe, every star, every living creature, every cup of coffee cooling on a table is fighting against the fundamental tendency of nature. The second law of thermodynamics says entropy increases, energy disperses, temperatures equalize. And yet, here we are. Warm, alive, thinking, creating pockets of order in a universe sliding toward disorder. And that's not despite the cold, it's because of it. The contrast between hot and cold, the gradient between warmth and the cosmic chill, is what makes everything interesting possible. If this perspective resonates with you, if seeing the cold has helped you appreciate the warmth, take a moment to like this video. And if you've stayed with us through this entire journey, subscribe. You're part of a community that finds meaning in understanding our place in this vast, strange, beautiful universe. Let's start with the most obvious source of warmth in our corner of the cosmos, the sun. Every second, the sun converts 600 million tons of hydrogen into helium through nuclear fusion. In doing so, it releases energy equivalent to 400 trillion watts. That's a 4, followed by 26 zeros. This energy radiates into space in all directions, and a tiny fraction of it, about 1/1000th, strikes Earth. That infinitesimal fraction is enough to warm our planet, drive our weather power photosynthesis, and make life possible. The sun has been doing this for 4.6 billion years, and it will continue for another 5 billion years before its fuel runs out. Think about what that means. For nearly 5 billion years, there has been a warm place in the solar system, a zone where water stays liquid, where complex chemistry can unfold at moderate speeds, where life can emerge and evolve. This warm oasis exists because of nuclear fusion, the same process happening in stars throughout the galaxy. Every star is a nuclear furnace, converting matter into energy, pushing back against the cosmic cold. Right now, there are hundreds of billions of stars in our galaxy alone, each one a beacon of warmth in the darkness. They won't burn forever, but they burn long enough for planets to form, long enough for life to begin. long enough for civilizations to rise and wonder at the universe that made them. But the sun isn't the only source of warmth for Earth. Deep beneath our feet, the planet itself is hot. The Earth's core, 6,400 kilometers below the surface, has a temperature around 6,000 degrees Celsius, roughly as hot as the sun's surface. This heat comes from two sources: residual warmth from Earth's formation, when countless collisions between planetesimals release tremendous kinetic energy and radioactive decay. Elements like uranium, thorium, and potassium in Earth's mantle and crust are unstable. They decay, releasing energy that's been trapped in their atomic nuclei since these elements were forged in supernovae billions of years ago. This geothermal heat flows outward, warming the planet from within. Most of the time, we don't notice geothermal heat. It's a small contribution compared to the sun's energy, but in certain places it becomes dramatically visible. Volcanic eruptions, geysers, hot springs. These are places where Earth's internal heat breaks through to the surface. Iceland, sitting atop the mid-Atlantic ridge where tectonic plates are pulling apart, has abundant geothermal energy. People there heat their homes with water pumped from underground water heated by the planet itself. It's a reminder that we live on a warm world heated not just by the star we orbit, but by the planet beneath our feet. And this internal heat has been crucial for life. Earth's liquid outer core, kept molten by geothermal heat, generates a magnetic field that shields us from solar wind and cosmic radiation. Without that magnetic field, Earth's atmosphere might have been stripped away billions of years ago, the way Mars lost most of its atmosphere. The warmth inside our planet isn't just comfortable, it's protective, creating conditions where life can flourish on the surface. Now, let's talk about life itself, because living things are extraordinary heat engines. Your body temperature right now is about 37 degrees Celsius, or 98.6 degrees Fahrenheit. You maintain that temperature through metabolism, breaking down food molecules, extracting energy, and using it to power cellular processes while releasing heat as a byproduct. This is true for all warm-blooded animals. We're constantly burning fuel to stay warm, fighting against the environment's attempts to cool us down. In cold weather, you shiver involuntary muscle contractions that generate heat. In hot weather, you sweat using evaporation to carry away excess heat. Your body is a sophisticated thermostat, constantly adjusting to maintain a narrow temperature range that keeps your proteins folded correctly and your biochemistry running smoothly. But here's what's remarkable. Maintaining warmth requires a constant input of energy. You need to eat because food is fuel. Plants need sunlight because photosynthesis captures solar energy and stores it in chemical bonds. Every organism is an open system, taking in energy from its environment, using it to create order, locally growth, reproduction, thought, while increasing entropy elsewhere by releasing waste heat. Life doesn't violate the second law of thermodynamics. It exploits it using energy gradients to power the complex processes that make biology possible. And where do those energy gradients come from? Ultimately from stars. The food you eat is made of molecules that came from plants, or from animals that ate plants, and plants got their energy from the sun. Even fossil fuels, coal, oil, natural gas, are stored solar energy, the compressed remains of ancient organisms that captured sunlight millions of years ago. When you burn wood in a fireplace, you're releasing energy that the tree captured from the sun through photosynthesis. When you drive a car, you're using energy from photosynthetic organisms that lived during the Carboniferous period. Almost every source of warmth on Earth traces back to the sun, either directly or through a chain of energy transformations. There are exceptions, though, and they're fascinating. In the deep ocean far from sunlight, hydrothermal vents spew superheated water from Earth's crust. The water can reach temperatures over 400 degrees Celsius, kept liquid by the immense pressure at depth. Around these vents, entire ecosystems thrive. Tube worms, clams, shrimp, and bacteria, none of which rely on sunlight. Instead, they use chemosynthesis, extracting energy from chemicals in the vent water, particularly hydrogen sulfide. These ecosystems are powered by Earth's geothermal heat, not the sun. They're proof that life can find warmth in unexpected places, that biology is resourceful enough to exploit whatever energy gradients are available. This discovery in 1977, when scientists first explored hydrothermal vents using the submersible, Alvin revolutionized our understanding of where life can exist. If life thrives in the darkness of Earth's deep ocean, surviving on geothermal energy alone, then perhaps it can exist on Europa or Enceladus moons with subsurface oceans heated by tidal forces. Perhaps cold worlds aren't sterile after all. Perhaps warmth, even a little bit of warmth in an otherwise frozen environment, is enough. Let's zoom out for a moment and consider warmth on a cosmic scale. Stars are the primary sources of heat in the universe, but they're not evenly distributed. In the dense cores of galaxies, especially in regions where new stars are being born, space can be surprisingly warm. The Orion Nebula, a stellar nursery, 1,344 light-years from Earth, contains regions where gas is heated to thousands of degrees by the intense radiation from young stars. These regions glow with their own light, visible through telescopes as colorful clouds of ionized hydrogen, oxygen, and other elements. Warmth isn't just about temperature, it's about energy activity change. And stellar nurseries are among the most energetically active places in the cosmos. But even between stars, even in the cold interstellar medium, there are tiny islands of warmth. Consider a cosmic dust grain, microscopic and drifting through space. If that grain passes near a star, it absorbs a bit of starlight and its temperature rises. For a moment, it's warmer than the surrounding space. Then it drifts away, radiates that heat back into the void, and cools again. These are transient pockets of warmth, brief and insignificant on cosmic scales, but they exist. The universe isn't uniformly cold. It's a mosaic of temperatures with warm spots embedded in a generally cold background. And here's something to consider. The expansion of the universe is making everything colder. The cosmic microwave background radiation, which currently has a temperature of 2.7 Kelvin, was much hotter in the past. When the universe was just 380,000 years old and the background radiation was released, it had a temperature of about 3,000 Kelvin, hot enough to glow visibly. As the universe expanded, the wavelengths of this radiation stretched, shifting from visible light to infrared to microwaves. Temperature dropped. By the time you're reading this, that ancient light has cooled to just above absolute zero. And it will continue cooling as the universe continues expanding. In 1 trillion years, the background temperature might be 0.1 Kelvin. In 100 trillion years, even lower. The universe is on a one-way journey toward cold, and we happen to live in an era when it's still relatively warm. But relativity warm means something different when you've experienced the cosmic scale of cold. Earth's average temperature is 15 degrees Celsius. Compared to the 2.7 Kelvin of space, we're blazing hot. Compared to the center of the sun, at 15 million degrees, we're freezing cold. Temperature is always relative. What matters isn't the absolute number. It's the gradient, the difference, the contrast. Life exists because there's a temperature difference between the sun and space, between Earth's core and its surface, between your body and the air around you. Those gradients drive everything. Have you ever thought about how strange it is that we perceive temperature at all? That evolution gave us sensors in our skin that detect heat and cold. It's because temperature differences matter for survival. Staying too cold means your metabolism slows, your cells stop functioning. Getting too hot means proteins denature, cells die. We needed to be able to sense temperature to navigate an environment full of thermal hazards and opportunities. The fact that warmth feels good isn't arbitrary. It's a signal from millions of years of evolution, telling you that this is the temperature range where you function best, where your ancestors survived and reproduced. And warmth carries emotional weight beyond its physical properties. We associate warmth with comfort, safety, love, a warm home, a warm meal, a warm embrace. These things matter to us in ways that go beyond thermodynamics. Psychologists have found that people who hold warm drinks judge others more favorably, that physical warmth can influence social warmth, that our metaphors for kindness and affection are saturated with temperature. Warm-hearted, a warm welcome. Cold-hearted, a frosty reception. Temperature has shaped not just our biology, but our language, our culture, our emotional lives. This connection between physical warmth and emotional warmth might actually have evolutionary roots. Infants need to stay warm to survive, and they stay warm by being held close to caregivers. Warmth becomes associated with safety, with being cared for. That association persists into adulthood. When we feel emotionally cold, lonely, isolated, uncared for, we sometimes literally feel colder. Studies have shown that people who recall experiences of social rejection perceive room temperature as lower than people who recall experiences of acceptance. Our minds and bodies don't fully distinguish between physical and social temperature. Warmth is warmth. So, what does all this mean for us having journeyed through the coldest places imaginable? It means that warmth is precious. It's statistically rare. Most of the universe by volume is cold, empty space. It's temporary. Eventually, all sources of heat will exhaust themselves. It's what makes complexity possible without temperature gradients. There's no energy flow, no life, no thought. And it's here now, surrounding us. The sun warming your face, the heat in your body, the thermal energy that allows molecules to move and interact and create the chemistry of life. Every moment of warmth is borrowed time, borrowed from the sun's fusion reactions, from Earth's radioactive decay, from the energy locked in the food you eat. Eventually, that energy will radiate away into space, the temperature gradients will smooth out, and equilibrium will win. But not yet. Not for billions of years. Right now, we're living in the universe's warm phase, the era when stars shine, and life is possible, and that's an extraordinary gift. Understanding the cold doesn't diminish the warmth, it amplifies it. It shows us that warmth isn't the default state. It's an achievement, a temporary victory over entropy, a local decrease in chaos purchased at the cost of increasing chaos elsewhere. And we get to experience it. We get to be part of the universe's brief, brilliant flourishing before the long fade to cold. So as we prepare to conclude this journey, as we ready ourselves to return from the cosmic cold to the warmth of here and now, we carry with us a deeper appreciation. We've seen where the universe has been and where it's going. We've glimpsed the absolute limits of cold and understood the quantum strangeness that emerges near absolute zero. And having seen all that, we can finally understand what it means to be here in this moment, in this warm and living world, in this brief window between the Big Bang's heat and the heat death's cold, a window where stars burn, where water flows, where consciousness emerges to contemplate the cosmos that made it. We've reached the end of our journey through the coldest places in the universe, and what a journey it's been. From the frozen plateaus of Antarctica to the quantum laboratories where scientists create temperatures lower than deep space itself. From rogue planets wandering in eternal darkness to the far future when the last stars will have burned out, and the cosmos settles into its final cold equilibrium. We've explored temperatures that span nearly 273 degrees, from the warm embrace of room temperature down to the haunting stillness of near absolute zero. But the most important discovery wasn't about cold at all. It was about warmth, about how rare it is, how precious, how improbable that we exist in this brief cosmic moment when the universe is still young enough, still energetic enough to support stars and planets and the delicate chemistry of life. We live in what future civilizations, if any exist, might call the stelliferous era, the age of stars. And we take it for granted because it's all we've ever known. Let me paint you a picture of perspective. Imagine the entire history and future of the universe compressed into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. For the first few minutes, the universe is unimaginably hot. trillions of degrees too hot for even atomic nuclei to form. By mid-January, the first stars ignite. Galaxies begin to coalesce. By early March, our Milky Way galaxy has formed. And on September 2nd, just over two-thirds of the way through the year, our sun is born, and with it, our solar system. Earth forms shortly after. Life appears in late September. Dinosaurs rule the Earth for a few hours in late December. Modern humans, our species Homo sapiens, appear at 11:54 p.m. on December 31st. All of recorded human history happens in the final minute before midnight. Now, here's the humbling part. If we extend that calendar to include the universe's far future, the era of stars, the time when fusion reactors like our sun illuminate the cosmos, lasts only until about mid-February of the second year. After that, for the remaining 10.5 months, there are no new stars being born. Existing stars slowly burn out. By the end of the second year, the last red dwarf has exhausted its fuel, and the calendar continues, year after year after year. Trillions of years compressed into this imaginary calendar, and almost all of it is dark, cold, silent. The era when the universe is warm and bright and interesting comprises less than 2% of the universe's total lifespan. We exist in that 2%. We are living in the universe's youth, its brief flourishing before the long decline into darkness. And that realization that we're here now, in the cosmic springtime, should fill us with something approaching awe. Here's what we learned from exploring the cold temperature. Isn't just a number on a thermometer. It's a measure of motion, of energy, of the fundamental jitteriness of particles that makes change possible. Cold is what happens when that motion slows. And absolute zero. The coldest possible temperature isn't just very cold. It's the point where motion stops, where quantum mechanics forbids any further energy extraction, where the universe says, no further. We can approach it, dance around it, get within billionths of a degree. But we can never reach it because the laws of physics themselves prevent us from achieving the perfect stillness. And yet, despite this fundamental limit, despite the universe's tendency toward cold and entropy and heat, death, warmth persists. Stars continue to fuse hydrogen into helium, pouring light and heat into the cosmic dark. Planets orbit in the habitable zones of their stars, maintaining temperatures where liquid water, that miraculous substance, can exist. Life emerges complex and beautiful, using energy gradients to build order from chaos. And somewhere on at least one planet, consciousness arises, looks up at the stars, and asks why. The answer we've found isn't comforting in the traditional sense. The universe is cold. It's mostly empty. It's heading toward a state where nothing can change and no life can exist. But the answer is also breathtakingly beautiful. We're here anyway. Against the odds, against the fundamental tendency of nature, pockets of warmth and complexity and life have emerged. You are one of those pockets. Your body temperature right now is about 310 Kelvin, a beacon of warmth, in a universe averaging 2.7 Kelvin. You're burning fuel, generating heat, maintaining order, pushing back against entropy. And you're doing it successfully, at least for now. This is what the physicist Erwin Schrödinger meant when he wrote in 1944 that life feeds on negative entropy. We're not just collections of atoms. We're processes, dynamic systems that consume energy and expel waste, creating local islands of order while contributing to the universe's overall slide toward disorder. We're temporary, yes, but we're real, and we matter at least to ourselves, at least in this moment. Think about the warmth you've experienced in your life, the warmth of sunlight on your skin, the warmth of another person's hand in yours, the warmth of a fire on a cold night. The internal warmth of your own body, that 37-degree sanctuary, where your thoughts and feelings and memories exist. Every instance of warmth is an act of defiance against the cosmic cold. Every moment of connection, every experience of comfort, every second of being alive is borrowed from the universe's temporary abundance of available energy. And when you frame it that way, when you understand that warmth is rare and precious and fleeting, it becomes almost unbearably valuable. I want to share something that cosmologist Carl Sagan wrote in his book, Pale Blue Dot. He was reflecting on a photograph of Earth taken by the Voyager 1 spacecraft from 6 billion kilometers away, showing our planet as a tiny speck of light against the darkness of space. He wrote, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves." It's a sobering thought. But he continued, "The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Like it or not, for the moment, the Earth is where we make our stand. And that existence on this warm island in a cold universe is extraordinary. Earth's temperature is maintained by a delicate balance, enough solar radiation to keep water liquid, enough atmospheric greenhouse effect to prevent runaway freezing, enough internal heat to drive plate tectonics and maintain a protective magnetic field. Change any of these factors significantly, and we'd be too hot like Venus or too cold like Mars. We orbit in what astronomers call the Goldilocks zone, where conditions are just right. But just right isn't a static condition. It's an ongoing process, a dynamic equilibrium that has to be maintained. Earth has been doing this for 4.5 billion years, and life has been part of that maintenance, contributing to atmospheric composition, participating in chemical cycles, helping to regulate temperature. This is the Gaia hypothesis proposed by James Lovelock and Lynn Margulis in the 1970s. The idea that Earth functions as a self-regulating system, with life playing an active role in maintaining habitable conditions. Whether or not you accept the strong version of this hypothesis, the basic insight is profound warmth and life are intertwined. Life depends on warmth, but life also helps maintain warmth, creating feedback loops that stabilize temperature within the range where biology can function. And now, for the first time in Earth's history, one species, our species, has become powerful enough to disrupt this balance. We're adding greenhouse gases to the atmosphere, changing the planet's energy budget, shifting temperature patterns that have been stable for millennia. In a very real sense, we're conducting an experiment. Can we alter Earth's temperature significantly and still maintain the conditions that allow our civilization to thrive? It's an experiment we didn't consciously choose to run, and we don't know the outcome. But understanding the nature of warmth, understanding how rare and precious and fragile it is, might help us appreciate what's at stake. Here's what gives me hope: we're the first species on Earth capable of understanding the universe at this level. We can measure the temperature of distant nebulae. We can cool atoms to billionths of a degree above absolute zero. We can predict the far future when stars will die and the cosmos will cool. We have knowledge that no previous generation possessed. And knowledge is a form of power, the power to make informed choices, to appreciate what we have, to protect the warmth that makes our existence possible. So, what do we do with this knowledge? How do we live knowing that we're temporary beings in a universe heading toward cold? I think the answer is with gratitude and care. Gratitude for the warmth we have, the sun that rises every morning, the planet that maintains habitable temperatures, the body that keeps itself warm through the miracle of metabolism, and care for the systems that provide that warmth, protecting the atmosphere, preserving biodiversity, maintaining the conditions that allow life to flourish. There's also something deeply meditative about understanding cold. When you grasp that the universe's natural state is near absolute zero, that warmth requires constant energy input, that everything warm is slowly cooling, it changes how you experience temperature. That cup of tea in your hands isn't just hot water with leaves. It's a temporary concentration of thermal energy borrowed from the sun through a chain of transformations soon to dissipate back into the environment. The warmth won't last, but it's here now, and you can feel it, and that's enough. This is what the Buddhists call impermanence, the recognition that nothing lasts forever, that change is the only constant. The universe's journey from the Big Bang's heat to heat death's cold is the ultimate expression of impermanence. Everything warm will cool, everything ordered will disperse, everything complex will simplify. But impermanence isn't nihilism. It's an invitation to appreciate things as they are in this moment before they change. The warmth you feel right now is real, even though it's temporary, perhaps especially because it's temporary. As we close this exploration of the coldest places in the universe, I want you to pause for a moment. Feel the temperature of your body. Notice the warmth. Recognize that you're a warm being in a cold cosmos, a complex structure in a universe trending towards simplicity, a conscious entity in a vast unconscious void. You're improbable. You're temporary. And you're here experiencing this moment, understanding these ideas, participating in the universe's brief awakening to itself. The cold. We've explored Antarctic ice, interstellar space, quantum laboratories. The far future isn't meant to frighten you. It's meant to contextualize the warmth, to show you that the ordinary miracle of being alive, being warm, being conscious, is anything but ordinary when you see it against the backdrop of cosmic reality. You are a candle flame in an infinite darkness, and that flame will eventually go out. But right now, it's burning. Right now, you're warm, and that's extraordinary. So, here's my invitation. As we part ways when you feel cold, remember what you've learned about the nature of temperature and appreciate the contrast that makes warmth feel so good. When you see stars in the night sky, remember they're fusion reactors fighting against the cold, and that your own warmth comes from the same nuclear processes. When you hold someone you love, recognize that you're sharing thermal energy. That warmth passes between you, that comfort has a physical as well as emotional dimension. Let understanding deepen experience rather than diminish it. The universe is cold, yes, but you're not. Not yet. Not for decades with luck. And in the time you have in this brief window of warmth between the Big Bang and the heat death, you get to experience everything that's possible in a universe with temperature gradients, life, thought, feeling, connection, wonder. You get to be part of the cosmos, awakening to itself, looking back across billions of years to understand its origins and forward across trillions of years to anticipate its end. You get to be warm. Thank you for joining me on this journey through the coldest places in the universe. Thank you for your curiosity, your attention, your willingness to explore ideas that stretch from quantum mechanics to cosmology, from the familiar cold of winter to the unfathomable cold of deep space and distant futures. I hope this exploration has given you a new appreciation for warmth, for the improbable gift of existing in this cosmic moment when the universe is still young and vibrant and full of light. If you found value in this journey, if these ideas have changed how you see the world, even a little bit, I'd be grateful if you'd share this video with someone who might appreciate it. Science isn't just about facts and figures. It's about perspective, about understanding our place in the vast scheme of things. And perspectives like this one deserve to be shared. We have more stories to explore together, more questions to ask, more mysteries to unravel. The universe is full of wonders, from the coldest temperatures to the hottest, from the smallest quantum particles to the largest galactic structures. Each topic is an invitation to see reality from a new angle, to appreciate the intricate beauty of the cosmos we inhabit. So, stay curious, keep wondering, and join me next time as we continue exploring the magnificent universe that is our home. Until then, stay warm, dear friends, in every sense of the word.